Okay, we have in the last video looked at the special case of constant acceleration. Again, the reason we do this is because we're going to encounter constant acceleration problems over and over again. And while we've talked about the graphs of constant acceleration, uh, we'd like a faster way of finding answers to constant acceleration problems. And for that reason, we're going to derive some equations, some very useful, simple equations that'll help us get answers about constant acceleration motion much faster than utilizing graphs. Again, the important thing to remember is we're dealing with constant acceleration motion only. And for simplicity, I'm going to assume that the initial position of this constant acceleration, x naught is equal to 0, and that the time of this initial of this constant acceleration motion begins also at t equals 0. Um, Here is a graph of velocity versus time for constant acceleration. The graph of velocity versus time should be a straight line graph, either sloping upward or sloping downward. And I can write an equation for this graph using the slope-intercept form. I know that v must be equal to v naught plus at, where v naught is the intercept and a is the slope of this graph. So this is one important equation that I can use for constant acceleration. Um, I know that for displacement, I need to find the area under the velocity versus time graph, and this area is a trapezoid. Now, I never can remember the equation for the area of a trapezoid, and so what I'm going to do instead is to approximate the trapezoidal area by this rectangular area, and I know I can do that if I make the height of this rectangle equal to the average of this velocity and this velocity here. That is, the height of this is equal to 1/2 v plus v naught multiplied by delta t will give me the displacement. Delta x is equal to 1/2 v naught plus v times t. Using the fact that x naught is equal to 0, um, delta x then becomes equal to x, and I have the equation x is equal to 1/2 v naught plus v times t. That's a second kinematic equation. Another way of getting the area of this trapezoid is dividing it up into a rectangular region as well as a triangular region. Now the area of this triangular region is 1/2 the base, which is t, multiplied by the height, which is v minus v naught. The area of the rectangular region is v naught times t. So the sum of these two quantities becomes equal to delta x. If I perform a little bit of algebra on this equation, I end up with delta x is equal to v naught t plus 1/2 at squared. And again, since x naught is equal to 0, I end up with the equation x is equal to v naught t plus 1/2 at squared. It's a third equation that I can use. So here are the three equations that I have so far. I'm going to do some algebra with these. I'm going to take the first equation and solve it for t. T is equal to v minus v naught over a. What I'm going to do is take that expression for t and plug it in here in the second equation. Now when I do that, I see I'm going to have this v naught plus v term. I also have this v plus v minus v naught term from the time. So what I have here in the numerator is v plus v naught times v minus v naught, and that you know is going to become v squared minus v naught squared. If I continue and do the algebra, I end up with an equation that says v squared equals v naught squared plus 2ax. So here I have four kinematic equations. Now the important point here is to recognize that we have five kinematic variables. They are v, v naught, a, t, and x, five kinematic variables. Now each of these equations involves four variables. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And in fact, each equation involves a different set of 4 variables. Now what this means then is that if I want to use these equations to solve problems, remember there are only 5 different variables, but if I want to use these equations to solve um, something involving constant acceleration, I must be given 3 quantities. If I'm given 3 quantities, I can use then any one of these equations to find a fourth. And once I have 4, I can use any of the other equations to find the fifth. So solving kinematic equations or solving problems involving constant acceleration is pretty straightforward. Read the problem. First of all, identify that the motion is motion with constant acceleration, um, and decide what 3 things you're given. You need to be given 3 things for this constant acceleration motion. Choose the appropriate equation to solve for the fourth, then use any of the other equations to solve for the fifth. It's that simple. That simple. Read, find out what you're given. Pick one of the equations and solve. Okay? So, kinematic equations. These equations, again, we're going to be using over and over and over again because we address motion with constant acceleration so frequently. It's one of the few things in this course that you will have to memorize. Fortunately, they haven't changed from last year, so you probably have them memorized from last year, and it won't take any effort at all to refresh your memory of these 4 kinematic equations, motion with constant acceleration. Okay.